Okay, so we should be good to go. So I'm going to review really quickly. We'll do one free response question with this method. Then I'll introduce how we can revolve around vertical lines instead of horizontal lines. We'll try one or two problems with that, and then we'll be done for the day. So everything we've done so far has been this method. So that's this one up over here on the left. The idea with this method is we're stacking these circular disks on top of each other. As we stack more and more of these disks on top of each other, we build a three-dimensional volume. If I wanted to make it hollow, I could cut a disk out of it. So that gives us our formula of one circle, pi r1 squared, minus another circle, pi r2 squared, from a start point to an end point in terms of x. Any questions on this method? Okay. I'm going to break out and we'll try one together. Okay, if you can't see on your end, let me know, and I can send you copies of all the files on WeChat as well. Okay, can you see? Cool. So I've got two functions. I'm going to call this y1 and y2. So our first function is root x. Our second function is x over 3. First, we need to figure out what the area of R is. So what do I need to do to find the area of R? R is the region bounded by these two graphs. So how do I find the area between these graphs? Okay, I need to subtract them. I'll need to figure out which graph is on top and bottom first, though. So I think what I'm going to do is we'll set these two graphs equal to each other to solve for the bounds. So that's the start point and end point for where these graphs meet. And then we can figure out which graph is on top. So let me do that really quick. So we are finding the bounds by setting y1 equal to y2. So that's the square root of x is equal to x over 3. Okay, I'm going to jump down here now. If the square root of x is equal to x over 3, what can I do to solve for x? Okay. Sure, I can times 3. 3 root x is equal to x. Okay, now what? Square root. So I'm going to square both sides. So if I square both sides, what's going to happen? (9x) equals x. X squared. Okay. So in order to solve these, I'm going to move all my x's onto one side. So I've got x squared minus 9x equals 0. Okay, what can I do now? Factor, okay. So if I factor, what can I pull out? X. Okay, so this will be x times awesome. So our bounds are x equals what or what? 0 or x equals 9. Perfect. Okay, so I know that my integral, when we integrate, is going to go from x equals 0 to x equals 9. Then I need to figure out which graph is on top. So I had y1 was the square root of x, and y2 was x over 3. So between x equals 0 and x equals 9, how could I figure out which graph is on top? Okay, so what number do you want to pick? So if I plug in 9, these are going to be equal, right? Since we already set these two equal to each other to get 0 and 9, so you can pick any number you want between 0 and 9, and that'll tell us which one's on top. 1, okay? If I plug 1 into y1, I'll get 1. If I plug 1 into y2, I get 1/3. So y1 is my top function, and y2 is my bottom function. Okay, so I think we have enough information now. If I want to find the area, what can I do? We're looking for the area between these two curves. Okay, we do minus them, so I'm gonna integrate okay, you said it. Integrate what? Yep, so I'm gonna integrate top minus bottom, you're right. X root 3. From what to what? From 0 to 9, perfect. Okay. Now I believe this was without a calculator. I don't actually remember. So we'll go ahead and integrate this directly. So if I integrate root x, that's the same thing as integrating x to the 1/2 power. So what will happen if I integrate x to the 1/2 power? X to the, I think that's a language difference, but 3/2 power. That's okay. So, in Korea it's flipped, right? Yeah, in Korea you read the bottom first. Okay, so 2x to the 3/2 power over 3. Minus what? Okay, x squared over 6. From 0 to 9. Okay, then I need to plug in my upper bound and subtract my lower bound. Okay, we can do that. So if I wanted to get a common denominator, This would be over 6, right? So this will be 4 and 6 instead. Okay, I'm going to plug in my upper bound. So it'll be 9 to the 3/2 power and 9 squared. What happens if I subtract my lower bound? Yep. What would my lower bound part be? Zero. Okay. So this something raised to the 3/2 power means you're going to take the square root and then raise it to the 3rd power. So what is 9 to the 3/2 power? Not 9. I'm going to take what's the square root of 9? 3, and then raise that to the 3rd power. 27, okay. Okay, so this will be 4 times 27 over 6 minus 81 over 6. 81 is what times 27? Three. So this is 4 times 27 minus 3 times 27. Should give me what? 27. So this is 27 over 6. Can we reduce that? Can we simplify? Okay, 9 over 2, which is our answer. Yes, for the first part. Okay, so our area was 9 over 2. Any questions on part A? Okay, I'm going to go ahead and, since we got a little bit of space here, I'll graph what we just did too. So we had two functions. We had the square root of x, and we had x over 3. That looked something like that. And they touched at x equals 0 and x equals 9. Okay, then we just found this region R, the area between them. Okay. So for part B, I want to find the volume of the solid generated when R is rotated about the line x equals -1. So for part B, I'm going to take this shape and we're going to spin it about x equals -1. So I'm going to redraw our shape really quick. This is everything we had last time. From 0 to 9. But this time I'm going to take this area that we had in R, and we're going to spin that around this line down here. Oops, highlighting. This line x equals -1. Oh, sorry. I'm spinning around a vertical line, x equals -1. My bad. Okay, so I'm going to move around this way. Okay, so we have not spun around a vertical line yet. So I'm going to take a break, and we'll talk about what our setup's going to look like. It's almost the same as our disk method, actually. So what I like to think about is almost a toilet paper roll. So if I wanted to get the volume of a toilet paper roll, so this cylinder with a hole in it, what I could do is I could cut this toilet paper roll into something like this. So if I cut down this line and unfolded the toilet paper roll into a box, then the volume of that box would be base times height times width, right? Okay. So when I look at, this is the unfolded this is the unfolded version, and this is my folded version, which was the cylinder. What would the equation be for the base of our cylinder? Right, 2 pi r. Okay, same thing. So 2 pi r, that's because that was really this circumference, the distance around that circle. Okay, each one of these cuts is going to be infinitely small. So this line here is really an infinitely small change in x, is the height of this box. So like the depth. And then this line here in yellow is the same as this line here. So that's my height. My height, which would be the difference between our two functions. So y2 minus y1. Okay. So in order to get the volume of this box, I do need a radius. That radius is my distance to the axis of rotation from where our box is right now, or this line that I'm drawing in green is the radius. Radius. Okay, so here's what it looks like for another example. I've got this space between y equals x squared plus 1 and y equals 1 that I want to spin around to the line x equals 2. So if I do, I'm going to have a radius, which is my distance from where the box is right now that I'm creating a cylinder out of. So that box I will spin around my axis of rotation to create a cylinder. Okay, so it looks something like this. I'm going to take this box and we're going to spin it around our axis of rotation. And create a cylinder out of it. So something that looks like this. And each one of those cylinders, each one of those cylinders is going to have a height, a radius, and a width that we can use to get the volume of that shape. And if we stack all of those cylinders on top of each other, we'll get the total volume that happens when we spun all of those cylinders around the axis of rotation. Okay, so I'm going to clear out my cylinder for a minute so you can see what's happening to the box we're about to spin. Okay, so if I zoom in here, this box is infinitely small. It's like a line, right? That infinitely small change in x is the width of the box that we will spin to create our cylinder. That height is my difference between our two y values. So that's x squared plus 1, or y2, and y equals 1, y1. My radius is this green line, my distance to the axis of rotation, which right now, if this axis is x equals 2, x equals 2 is this line here, then this green line is going to be whatever our x value is right now, subtracted from 2, or this green line is really 2 minus x. Okay, so that gives us our radius and our height and our width. Oops. Sorry, that axis isn't 2. That axis is x equals 4. Okay, let me go back. So, can't read apparently. This is x equals 4. This is x, our distance to our box right now. So that means that this green line is really 4 minus x. The difference between those two x values. Okay, so that gives us our radius is 4 minus x. Our width of the box was dx. And our height of the box was x squared plus 1 minus 1, which is x squared. Okay, so here's what our shape looks like, our toilet paper roll. If we unfurled that toilet paper roll, I would get a box with a change in x for my width, a height of x squared, that was the difference in my two y values, and a base of 2 times pi times my radius, which was 4 minus x right now. And if we kept stacking all the possible cylinders, so every possible line, from 0 to 2, and use those to create cylinders, then we would end up with a shape that looks like this. As you spun around, so kind of like a volcano, almost. A cylinder with a hole in it. So the volume of that volcano would be this. That's 2 pi r, or the base of this shape, times my height times my width. Okay, do you understand how we built it? Okay, I'm going to show you one more construction here. Okay, so this time we're looking at the right side with shell method. So on this right side, I have, not moving, there we go. Okay, on this right side, I have two lines. Our top line, y equals x over 2, which is this line here. And then our bottom line, y equals x minus 1 squared, which is this function here. So what we're doing is we're taking the difference between those two lines to create a height, our dx to create a width, and then our distance to the axis of rotation, our distance to 0, to create a bunch of cylinders. And if we stack infinitely many of those cylinders together, we'll end up with a 3D shape. Okay, do you understand what's going on? Okay, so we'll see if we can build one with the AP question then. Okay, so for our function, we had y equals root x, and y2 was x over 3. So I'll zoom in. This is y1 equals the square root of x, and y2 equals x over 3. I wanted to take this space that's in the middle, so this region R, and spin that about this axis of rotation. After we spin that about the axis, I'm going to end up with a shape that looks like this. That's hollow. Okay. So how we're going to set it up is I'm going to have a box that we are going to constantly move from x equals 0 to x equals 9. So we'll build up infinitely many of these boxes, that we will spin around our axis of rotation to create this cylinder. So every cylinder is going to have a change in x, a height, and a radius. Okay, so first, the hard part. What would the radius be? Okay, x is this distance. Then I also have to get to the axis of rotation, which is currently at x equals -1. So what do I have to add? +1, right? Because I've got an extra 1 unit to get to x equals -1. Okay, if you're not sure, we could take our x value where we are right now, x, and subtract the x value we want to go to get the difference between them. So that would be x minus -1, which is x plus 1. Okay, then I need the height of that box. So what's the height right now? It's based on my y values, but I have two y values. Okay, so okay, not x squared, no. So I've got my height right now is can I point? My height right now is this line, which is my my difference between the red line and the blue line. What's the equation of this red function? Root x. Okay, so I've got root x. And then if I want the difference between them, I would need root x minus what? X over 3, that's it. Okay, I've got the radius, the height, and then the last thing I need is the width. So that width is going to be dx, right? You're way ahead of me, but if I zoom way, way, way in, then that width is going to be this infinitely small change in x. All right, any questions on our setup? Okay, so once again, after I unfurl this cylinder, this base you told me would be equal to 2 pi r. This width you told me would be equal to dx, and this height earlier you told me would be equal to the difference in our y values, y2 minus y1. Okay, so if I wanted to set this volume up, my volume would be equal to base times width times height. So that's 2 pi times our radius, x minus 1, times our height, root x minus x over 3, times our width, dx. Now, I'm going to have infinitely many of these cylinders, infinitely many of these volumes that we are stacking on top of each other between x equals what and what? Not negative 9. X equals 0 to 9. All right. And we are ready to find the volume. Any questions on our setup so far? Okay. I'm going to zoom in here and we'll solve this integral and we'll be done for our volume. So if I want to solve this, what's the first thing that I need to do? Plug in. Okay, so before I can integrate, I'm going to need to simplify this a little bit. So what happens if I multiply x minus 1 times root x minus x over 3? Okay, I'm going to multiply them. So what happens when I multiply? You're right, I actually had a mistake there when I wrote that line. So plus root x minus x over 3. Okay, cool. All right, so now we're ready to integrate. I think I'm going to simplify this term one more time. So just change our roots to powers so that we can integrate this with power rule a little more easily. So this is x to the, this would be 1/2 times x to the 1 is x to the 3/2 power minus x squared over 3 plus x to the 1/2 power minus x over 3. Okay, so what will happen when we integrate? Awesome. What power? Cubed, yeah. It was a really good job with those fractions. I know it's hard with English. Okay, so then going from 0 to 9. Okay, once again, for that lower bound, when you plug in 0, you're just going to be subtracting 0. So we're only worried about plugging in the upper bound. Okay, so my volume is 2 pi times all of this. I'm going to plug in 9. If I plug in 9, this bottom part of the fraction tells me I'm going to square root 9. So the square root of 9 is 3. So this is 3 to the 5th power. Minus 9 cubed over 9 plus the square root of 9 is 3, cubed is 27. 2 times 3 cubed over 3 minus 9 squared over 6. Okay. So we'll try to simplify. I'm going to simplify as much of it I can from these fractions before we get the common denominator, and maybe that'll make it easier for us. Okay. Any idea what 3 to the 5th power is? 243 times 2. Okay, so I've got 486 over 5. Unfortunately, none of that reduced, so I'm going to keep it just like that. This one, though, minus 9 cubed over 9 is the same thing as 9 squared. So that's minus 81. Okay, this 3 cubed over 3 is the same thing as 3 squared times 2 is 18. Then I've got 9 squared, so that's 81 over 6, but I can reduce that. So what would 81 over 6 reduce to? (27 over 2). Okay, perfect. So then I'll have to get a common denominator so I can add these all together. I'm going to go ahead and add these constants together first, I think. So what is negative 81 plus 18? Yep. Okay, minus 27 over 2. I guess we'll go ahead and get a common denominator now then. What's our common denominator? 10. So my volume is 2 pi times. Okay, I'll have to multiply by 2 for this one. So what's 486 by 2? And 72 over 10 minus 630 over 10 minus what? Okay, I've got 135 over 10, I think. 27 by 5, right? Okay, then I'm going to subtract. So let's just go one at a time. 972 minus 630 is how much? Okay, so we got 342 minus 135. $207, okay. And then the last step, this 2 and the 10 can cancel. So my final answer is going to be what? It's perfect. Okay. I kind of ran into my C space down here, but any questions on how we got the volume? All right. I'm going to skip part C for now because we only have 15 minutes left. And we'll see if we can set up another. Yeah, go for it. Okay, so last one for today, and then we're done. So I've got these two lines here, y equals the natural log of x, and y equals x minus 2. Now this time they were nice enough to give us a graph. So if this is our graph, which function is our top function right now? Okay, so this one here, which I'm going to redraw in red, is y equals ln x. And this one I'm going to redraw in blue. X minus 2. Okay, I'm going to call this y2, and our red one will be y1. Okay, so what would I need to do to find the area of R? We find the bounds. Now, this one was a question with a calculator. So I'm going to pull up a calculator and we'll use that to find the bounds. Okay, so in my calculator, in order to find the bounds, I'm going to graph both of these functions, and then we'll calculate some intersects. So let me do that really quick. This is the natural log of x and x minus 2. So if I graph these, we've got our two functions here. Do you remember how to calculate an intersect? Okay, so we're going to go to second and then calculate. And then scroll down to intersect. So our calculator needs to know a couple things. Because you could have 10 of these graphs graphed at the same time. It needs to know what two curves that you want to intersect. So if I show you with the cursor here, I can move right or left so you can see which function you're on right now. I can move up or down to change functions. Now we only have two functions graphed, so there's not really much choice for us, but I'm going to tell the calculator my first curve is this one on top, so I'll hit enter. And then my second curve is this one on bottom, hit enter. And then a guess. Now there's more than one intersect for these functions, so it needs to know which intersect we want. So once I hit enter, whatever the cursor is closest to, it'll give me the intersect that's closest to that cursor point. So if I move way over here to the left, and then hit enter, it'll give me an intersection point that's closest to where I was. Okay, so here's one of our intersects at y equals 1.146. Okay, I don't want to move anything, so before I touch anything, I'm going to hit second quit, and then x store as alpha. I'm going to call this b since that was our right one, and hit enter. Okay, so now I've got that point, my intersection point that I won't have to round for. Okay, I'm going to go ahead and mark that here on my paper too. This is 3.146193221. B equals 3.141. Oh, sorry, 3.146193221. 6193221. Okay, now that I've labeled this as B, I never have to write that decimal again. I can just write B for all the rest of my work. Okay. But I am going to store that in the calculator that we were not rounding, and our answer won't be wrong since we have to be right to 3 decimal places at the end. Okay, I'm going to go back to my graph. So I'll hit graph and calculate my other intersect. So second calculate and intersect. So once again, I've got my first curve, my second curve. This time I'm going to move my cursor over to the left and hit guess. And I've got my second intersection point at x equals 0.15. So once again, second quit x store alpha a. So a is 0.1585943,396. 0.1585943,396. 943,396. Okay, I've got our intersects, which from now on we can just call A and B. Since we've told College Board we know what A and B are. Okay, so if we know what A and B are, how can I find the area of R? ln x minus, in parentheses, x minus 2. Okay, and then I need something else. Okay, I'm going to integrate from what bound to what bound? From A to B, perfect. Again, I can just cite A and B now that we've defined them. And then I'm integrating in terms of what variable? In terms of x, perfect, dx. Okay. So if I simplify, that's the area is equal to the integral from a to b of ln x minus x plus 2. Dx. Okay. Again, we do have a calculator for this one. So I'm going to do this in the calculator. And I actually already have, if I show you, y1 is ln x, y2 is x minus 2. So I'm going to integrate using that. So that's math integrate. Our equation, variables, y variables, function y1, that's my natural log, minus variables, y variables, function y2. So top minus bottom, comma. So that was my equation. Then I need my variable, x. From my lower bound to my upper bound, from A to B. And now we're not rounding, and we've got our equation top minus bottom. Okay, if I hit enter, and that's my integral. Okay, so our area was equal to 1.949. 090927. 1.949. 090927. Okay, any questions on our setup? Okay. I've got less than 4 minutes left, so I think what I'm going to do is I'm going to leave you with part B and C, and that's the part that we'll actually grade. I'll also flash the scoring guides here so you can see how they would have given you points for this. So I'll go back and do that for the first part for A and B. And then I don't think I can show you the scoring guide for the other one yet since I've just assigned that for homework, so my scoring guide for this one. So they gave 1 point for your limits, 1 point for the integrand, and 1 point for your answer. So I'll point that out. Your limits are the constants of your integral. So if you wrote an integral from 0 to 9, you would have gotten this 1 point. Your integrand is your setup on the inside. So that's top minus bottom in terms of x, would be another point. And then 1 point for your answer of 9/2. Okay, for part B, they had 1 point for constant and limits. So that's 2 pi on the outside from 0 to 9. They had 2 points for your integrand, which I assume was 1 point for the radius part and 1 point for the height part. 1, 2. And then 1 point for our answer, which, check. Answer was 207 pi over 5, which is what we got. Okay, every AP question is out of 9 points total. We did not do part C. We did not do part C, but we've already got 6 points out of 9 so far, which should be enough for a 5. Yeah. I guess I'll set up this last one then, since we've got 2 minutes left. So if this region R, this distance, this area between root x and x/3 is the base of a solid, and cross sections perpendicular to the y-axis are squares. So if my cross sections perpendicular to the y-axis, so perpendicular to the y-axis are squares. I wanted to find the volume of the solid. So if my cross sections perpendicular to the y-axis are squares, and then that means I've got a dy here. If I'm perpendicular to the y-axis, then this would be my change in x. So that's x2 minus x1. And it's a square, so this is also x2 minus x1. Okay, so then my volume would be x2 minus x1 squared times dy. Okay, so I'm gonna write it out really quick. Get rid of this so I'm not messing up Oliver for part A, but okay. So down here in part C somewhere, this would be our volume is equal to the integral of x2 minus x1 squared in terms of y. Now I am integrating in terms of y this time, not in terms of x. So if I jump back up, if I'm normally integrating from x equals 0 to x equals 9, then my y value will be 9/3 is 3. For this one, my y value would be 0/3 for this one is 0. So I'm integrating from 0 to 3. And then I'm going to rechange these y values into x values for both of our functions. There we go. Okay. So my first one was our top function, which was root x. So if y1 is equal to the square root of x, then x1 is equal to y squared. And then for y2 is equal to x2/3. So that means x2 is really 3 times y. Since we're moving up in a line, our y values will always be the same. So I could rewrite our formula for volume as the volume is the integral from 0 to 3 of x2 minus x1. I want top minus bottom, so this is actually my top. So this is y squared minus 3y all squared in terms of y. Okay. Which, if you solve, ends up being 8.1. Okay, on their scoring guide, they had 2 points for this. 1 point was the integrand, and then 1 point was the answer of 8.1. Okay, any questions on anything from today? Okay, so what I'm going to do is I will send you this file that we've started on WeChat. I need you to go back and complete part B and C from 2006, and then turn that into me Monday during Wildcat time, or before school, if you just want to drop by. I will post this video to YouTube, so if you want to go back and see the video, you can. Along with all of the files we use today through WeChat and Skype. All right, thank you so much for coming, and I will see you on Monday.